So just to review, let's list all the properties of chaos. And first of all and foremost, it's irregular, which we defined as aperiodic. Never closes, has no period. Second point, it's deterministic. Now, in the case of a mathematical model, as I said, in the case of a mathematical model, that's easy. Namely, was the behavior produced by a mathematical model? Yes. Did the mathematical model have any noise inputs to the system? No. Then the irregular behavior is definitely chaotic. But this is going to become an issue in real-world systems, which is going to be our next topic. But for right now, we say in the math, it's very easy. X prime equals f of x, or xn plus 1 equals f of xn. These are deterministic processes. The third property is that it's bounded, which creates all of that complexity. The fourth property was sensitivity to initial conditions, the so-called butterfly effect. And that's what makes the system so difficult to predict in detail. We also said that chaotic behavior is, in fact, governed by attractors. These are chaotic attractors. And these are now the third kind of attractor after equilibrium point or point attractors and limit cycle attractors. The third category is now chaotic attractors. And this attractor, which you saw, for example, in the food chain model, shows us what is happening in the system. This oscillates and that gets bigger until that crashes. The attractor picture tells a story, and the story is how is chaos happening in this system. We also talked about causes of chaos. Remember, in the discrete time system, getting yo-yoed, getting hit like a tennis ball between the growth phase and the declining phase produces this irregular behavior. We talked about parameter-dependent transition to chaos. That is the route to chaos. And finally, we mentioned, apropos of this thing about being deterministic, we mentioned that in a chaotic system, the irregularity which is generated internal to the system and not imposed externally on the system. So this gives us a clue. This number 2 here gives us a clue to the all-important question, which is how do we diagnose chaos for a system that we come upon in nature? So the question is, how do we diagnose chaos in nature? We come upon a system in the lab or in the field or in the world, and it's behaving irregularly, and we want to know, is this irregular behavior random or is it true chaos? Now, we already saw an example. Remember, I was mentioning the kind of fanciful example but not really, of I want to try to arrive at work every day at exactly 9 o'clock. If you look at my actual arrival times, they are a scatter around 9 o'clock. Nobody arrives at exactly 9:00 every day. So we're going to have a scatter of points around 9. And the question is that scatter random or is it chaotic? And the answer is it could be either. And the way to tell the difference is simply to take the data and let the data be arrival time on day 1, arrival time on day 2, arrival time on day 3, and then plot that data. And now this is not a mathematical function anymore. This is just a data set. I could have walked in and handed you this data set. And what you would do with this data set as a diagnostic is to plot Tn plus 1 against Tn. And then the diagnostic is very straightforward. If this really was a random process, for example, traffic lights and other drivers and pedestrians and car problems and all of that, then this plot is going to be a blob, because that's exactly what you would see if you flipped a coin each day to determine the error plus or minus at around 9 o'clock. If you made a graph of that, it would show the characteristic sign of randomness, which is a point blob. But if it wasn't, and I was talking about the mechanism where if I'm a little early one day, then I overcorrect a little bit and I come a little late the next day, then that data could easily trace out what I'm going to call a non-blob. That is a low-dimensional figure derived strictly by plotting Tn plus 1 against Tn. And this is the sign of a chaotic system that is generating its own variability.